So hi everyone, thanks for coming. Hello people behind the pillar that I can't see. Hopefully you can see some slides. So my name is Alex, and together with my co-authors, I'm from the University of Washington, and together with my co-authors I'd like to present SwitchBack, Guiding Users' Attention for Mobile Task Resumption. Now before I jump into our actual system, I'd like for us to do a quick comparison of laptops versus mobile devices. Both of these are portable, but they're portable in different ways. When we think about laptops, we take them to different places like conferences and cafes. But when we use them in one particular location. And because of that, we can make assumptions about the environments in which they're used. For example, they tend to be stable because we don't walk around with them. We put them on a table. We have consistent lighting. And assuming we don't have an annoying coworker, they're usually free of distractions. Once we use mobile phones, however, these assumptions can break down. And we could be using them in environments that are full of motion, have variant lighting, and are full of distractions. Due to these changing... Sorry. There is a slide missing. Okay. Well, due to these varying conditions, we encounter what are known as situational impairments, or factors that inhibit our abilities to perform certain tasks. For example, if you're in a rainy environment, it makes it difficult to use the touchscreen. If you're walking around in a busy metropolitan area, it may make it difficult for you to look at your phone and send a text message. So I'd like for you to imagine this particular scenario. Hold on. Okay. The video is not playing, so I will just describe the situation. So what would be happening in this video is, imagine that you're sitting on a bus and reading an article, and you notice that you've reached your stop. What you'll tend to do is you have to look away from your phone, and you encounter what is called a situation of divided attention. And you have this contrast of attention between the activity that you're performing, which is reading, and dealing with your surroundings. And when you come off the bus, it makes it difficult for you to return to your task because of this increased cognitive load. So what SwitchBack does is, rather than having you look through the article, we can focus your attention into a particular location so you can return to what you were reading in the article. So we see SwitchBack as borrowing from two related works that are hopefully well known to the community. The first is Phosphor, which was proposed by Bowdish et al. From US 2006. And what they did was they realized that user interfaces are very complicated, and it makes it difficult for people to maintain their attention to lots of small changes. So what they did was that they highlighted changes to interfaces with these green highlights. For example, as the user moved the volume from that high setting to the low setting, they show this green highlight to highlight that difference. So we actually borrow this highlighting technique for our own purposes in the context of reading. The second work we borrow from is iPhone, presented by Emiliano Meluzzo in Mobile 2010. And they use eye tracking in an active approach, sort of as an input. So if you think about a mouse, the gaze corresponded to the movement of the mouse pointer, and then a click corresponded to a blink. So they use gaze in an active sense, and they realized that using this absolute gaze position was noisy when the face was far away from the phone. So rather than using it as an active component, we're going to be using gaze as a passive metric for interest in a particular content. In fact, this notion's been brought about as early as 1967 by a gentleman named Alfred Yarbus. He asked for people to mount themselves in that very scary-looking device, which is actually an eye tracker. And he had them observe paintings such as this one on the right. And those white lines indicate how people looked at this particular painting when he asked a particular question. For example, he would ask, who are the people that are talking in this room? And you could see that the users are looking at these two figures mainly. When looking at the gaze pattern across the painting, he noticed that there were two different sort of interactions. The first are these fixations, where the eye pauses and focuses on a particular point. And the second are saccades, or big gaze jumps between these different fixations. In short, what he realized was that interest manifested itself in the gaze trajectory. And this is what we use in the context of reading. So we developed what is called the Focus and Saccade Tracking technique that is underlying our SwitchBack system. In particular, it's meant to answer two particular questions. Is the user looking at the screen? So are they focusing on the phone, or are they dealing with the surroundings around them? The second question it answers is, how is the user looking at the screen? We aren't looking at absolute position, but we're looking at whether the user is looking towards the right, left, top, or bottom of the screen. And a question that underlies all of this is, can we do this with current front-facing cameras on the smartphone without any hardware modifications? So how does this work? I looked younger back then. You can see that computer vision techniques have been working for quite some time. So we use face and eye detection to monitor whether the user is looking at the screen. If you need more details on that, there's lots of great work in the computer vision community, or I can go over some vague details. If we look at the eye in particular, we can look at the location of the pupil relative to the coordinate space of the bounding box of the eye. And we can actually map which direction the user is looking in based on this coordinate system. For example, if you look at the 0 on the x-axis and the pupil is towards that side, that means that the user is looking at the right relative to this direction. Now, if you look at this in the context of reading, we could see that the eye moves from the left side to the right side very slowly, and then makes a quick jump to the left side of the screen. And it's this sawtooth behavior that we observe for our own system. So this is what the signal could look like. On the bottom, I have the right horizontal gaze position, and on the top is the left. And we can see that the signal tends to be noisy. Eye trackers aren't perfect, especially in noisy conditions, such as walking. So the first thing we do is we smooth the signal using a low-pass filter, and we detect the peaks and troughs in this signal. And these are actually those saccades that were mentioned earlier, those gaze jumps. Because we're looking at reading, we're only interested in the moments when the eye moves from the right side of the screen quickly to the left. In this case, we're only interested in the troughs. So this was a semi-ideal condition. Like I said, eye trackers can be noisy sometimes, and we might get an even worse signal. But there's something better that we can do than just low-pass filtering. Let's say that we know that the trough at the bottom left over here is a correct line jump. Based on information that we know about the reading and the amount of text that the user is reading, we can make some assumptions of approximately when we should expect the next line jump. So if the user is going to be reading more content, then we would expect the next peak to be further away. So in this case, this peak that's over here at the top happens way too soon. So we assume that this is a false positive, and what we can do is simply ignore it. This next trough happens relatively in the correct range, so what we'll do is we'll say that this is in fact a correct new line, and we can move this window over to the next stage. Now here we detect a trough that is what we consider to be too late. So what we can do is that we know that we were expecting some sort of trough in between, so we had a false negative, and we can interpolate over here and continue counting the number of lines from there. So in this case, even though we saw 4 different troughs, they were in the wrong locations, we can correct it by detecting these false positives and false negatives. So we evaluated this technique on its own in a user study where we asked people to read 20 lines at a time. We had 8 participants, and we had a 2-factorial design where we asked users to either read while standing or walking on a treadmill. And this treadmill is meant to simulate some of the conditions that will be met in an outdoor environment where you're walking and the camera's jostling, and it makes it slightly harder. So the results, we had an error that was less than a line per 20 lines that the user read. We tended to overestimate the number of lines that were read, meaning that we had more false positives than false negatives. And we found no statistical difference for people wearing glasses versus not wearing glasses or posture. So the glasses versus not glasses mainly has to do with the eye detection, gaze tracking algorithms. The posture has to do with the algorithm and how we handle for the noise. So how do we apply fast to SwitchBack with the video that you didn't get to see? Pretend that you're reading a body of text. Using the algorithm I've just described, we count the number of lines that the user has read corresponding to those troughs. When the user looks away, we store this information. Once the user returns their gaze back into the screen and we can detect their face and eyes, we highlight the line that they were last looking at. Once they continue reading again, we slowly fade away that highlight and continue the line counting algorithm. And we repeat this process for every distraction that the user encounters. So on our evaluation here, we have 17 participants. So we evaluated this technique with 17 participants, 9 males, 8 females. And this was a more complicated study, 2 by 2 by 2 factorial design. So first we have this standing and walking condition where, yet again, the user was standing on the treadmill, walking on the treadmill or standing. We have this distraction versus non-distraction. So we incorporated distraction to bring about this case of divided attention. I'll describe in a couple seconds. And then we have switchback versus a controlled decision, so whether we incorporate this highlighting or not. So what's this distraction that I was describing? It may be difficult to see, but we have 2 screens, one on either side of the user. And what we did every minute to minute and a half is that we would show 13 letters on the screen, some combination of T's or L's in a rotation. And this was a distraction task that was inspired by Yokoyama et al. From Scientific Reports 2014. So we asked the users to count the number of T's or L's, and once they did that, they could return back to the reading task. So in this case, there were, I always forget the number, 6 L's and 7 T's in this case. So does everyone understand the distraction task? I hope you do, because now I'm going to ask you to do it. I will be showing the number of letters for about 6 seconds. Don't yell out your answer yet, but keep it in your head. Ready, set, beep. Okay? Now, the funny thing is that if you weren't paying attention to my talk and you were looking away from your screen, then you're actually demonstrating the sort of situations we're trying to handle, the situations of divided attention. So how many of each letter was there? I heard 8 and 5. So 8 L's and 5, 5 L's and 8 T's. If you did that, high five. Come give me a high five later. So in order to evaluate this, we use the reading speed as our metric. Everyone was reading the same number of words, but the amount of time that the user spent was something that we were looking at. The reason being is that if you're distracted and you find it difficult to balance the cognitive load between the 2 tasks, you're going to take longer trying to figure out where you were in the body of text. So we expected higher reading speeds when people were using switchback. So these are what the results looked like. So when people weren't performing the distraction task, so they didn't have to turn their attention away and they're just reading, we had a less than 1 word per minute difference. So this made sense to us. There's no reason for people to be turning away. They're just reading. In the presence of distraction, we see a reading speed increase. They improve by 8% or 19 words per minute in the presence of distraction using our application, which means that we're successfully guiding people's attention back to the line that they were last looking at and able to quicker resume reading. So there are a couple limitations to our work. The first thing that we noticed was that the face wasn't always visible. Some people didn't recognize that they were using the front-facing camera, so they would cover it with their thumb or they would turn it away. We could give them feedback about what the camera sees relative to their face, but we found that that would actually be distracting and add noise to the sawtooth behavior of the signal that we were expecting. One solution to this would be to use a device like the Amazon Fire, which has multiple front-facing cameras and likely a wider field of view, so that in case of someone's blocking one camera, you can use the others. Another limitation that we encountered was different reading behavior. So we're assuming sequential reading. You're reading one line after the other, but that's not always the case. Sometimes if you're reading something that you're not very interested in, you'll just skim through it and read very quickly. Or if you don't understand material, you might jump back and look at what you were previously looking at. So there's a couple things we can do here that we haven't done yet, but we're looking to do in future work. One thing we can do is learn the reading speed of the particular user. For example, if the system uses a very wide range for those windows I mentioned earlier in the FAST technique and learns that the person tends to be reading very quickly and we have lots of false positives, we can narrow down the window in those higher speeds. Similarly, if we know the content that the user is reading, we may be able to predict whether the user will be bored and read quicker than expected, or we can even maybe be able to predict that the user will be confused and have to go back and account for that in our algorithm. So in conclusion, our FAST technique monitors when and how the user is looking at the screen, and when we're assessing these situations of divided attention, switchback improves reading speed by 8% in the presence of distractions. And with that, I'll conclude and say thank you.
Yep, I'm Ring-An Lo from University of Washington. Do you mind flipping back to the slide that has the comparison between the two conditions?
Sure.
How is the words per minute measured here? What this is telling me, I believe, is that I should try to be distracted while using SwitchBack, and I'll read faster than if I'm not.
So we time the amount of how long the user spent completing the distraction, and we subtracted that from our words per minute. So we're only accounting for specifically the amount of time the user spent reading.
Okay.
So the additional time that's reducing the reading speed in the control condition, or at least that's what the hypothesis was, that the extra time is accounted for the fact that the users are looking for where they last were. But the distractions we filtered out and we don't account for in the reading speed.
Did you compare the SwitchBack under distraction to either the conditions where they're not distracted? Because it seems very strange that you would read more words per minute if you're distracted.
Oh, you're talking about from the SwitchBack with the distraction?
Yeah,
so this is really weird. You could tell we have big error bars.
Sure.
There's a lot of factors at play. Some of them include, we had people who just said, oh, I was bored with the article and I just skipped most of it. And we were into all sorts of conditions. So it is kind of weird.
It's probably down to noise, right?
Yeah, so we think it's due to noise. It's something peculiar and we don't have an exact explanation for.
Okay, cool, thanks.
Mm-hmm. There's one more.
More of a suggestion, really, that might be useful for you. I've been doing a lot of reading of the mind-wandering literature, and there's some they're showing pupilometric evidence for inattention or episodes of mind-wandering.
Mm-hmm.
I don't know if that's like being able to measure pupil diameter might be something you could do with the camera phone, but.
Yeah, so one of the things that you have to deal with is resolution of the cameras. And certainly when these eye tracking algorithms get better, then we can rely on more accurate measures. So for instance, we didn't even use the vertical gaze at all, looking at the vertical coordinate, because it was so poor at far distances. So ideally, if we have super cameras and we can look at things like pupil dilation or even just the vertical gaze position, we can improve our algorithm. This is just meant to, even with really poor cameras or poor algorithms, we could still do something with them.
Okay, sure.
But yeah, thank you for the suggestion.
No problem.